Hi everyone. Today I would love to talk to you about the reaction rate as a function of concentration and temperature. I wanted to give you an intuitive approach as it is a recurring subject in IB chemistry, both SL and HL questions. However, a lot of people struggle with understanding it intuitively. And yet the intuition behind it is very approachable. So you already know from the lessons that the reaction rate, which is of course how quickly a reaction proceeds, changes with the change of concentration and the change of temperature. Let's think of some kind of a benchmark reaction. Let us consider one of the simplest kinds of reaction, which is A plus B going to some product C. We do not really care what is the product C. We can only, for now, assume that it's unimolar, so that 1 mole of A and 1 mole of B would give you 1 mole of C. This is a tabletop reaction of some kind of a condensation or, in general, a synthesis. For example, as in the hydrogenation of 2-propene over palladium catalyst, which of course gives us just a simple propane. Oops, like that. So let us think of this reaction as by imagining some kind of a ballroom. In this ballroom, we will consider some kind of a reaction. Well, to have a reaction, we need to have the reagents. Let the reagent A be the gentlemen dancing, and the reagent B would be the ladies dancing. And the reaction that we consider is when a gentleman and lady meet in the ballroom and they start dancing together, which is kind of a typical situation in some ball halls, as in, for example, Vienna. So we already have defined our reagents, we already defined our product, so the product is the pair dancing. We can consider it as a new chemical compound. And let us also imagine that they walk around this ballroom randomly. So their motion is completely random, like that, and each person moves absolutely independent on each other. We can imagine that if the ballroom is huge, there is, let's say, only 2 ladies and 2 gentlemen walking around, trying to find each other to dance together. The chances for them meeting will actually be pretty low. If you kind of try to scale down the image, let's try to imagine that they are much smaller in relation to the whole ballroom, and for them to stumble upon each other and start dancing together is not very likely. Now, what can we understand as temperature? We know that the temperature is the average kinetic energy of the molecules, and we of course know that kinetic energy will be well proportional to the velocity, or in general the speed of the particles. So let's kind of try to imagine the temperature as the music and how quickly the music plays. We know that if the music starts playing faster, the people would also start moving a bit faster. So as the temperature increases, so as the music starts playing faster and faster, we may imagine the people to also move a bit faster. So what happens is that at some point they can meet each other in a much quicker way. Let's try to think of 2 scenarios. Let's draw 2 simple boxes like that. In one case, the motion is very slow of each of the people. So if the motion is slow, the likelihood of them meeting at a certain time point is also much slower. But if someone moves much faster, just like that, you can already see from the drawing that these 2 lines met up much more quickly. So if people are dancing more and more vividly, they will stumble upon each other in the ballroom much more quickly. Now, how does it translate to concentration as well? Let's try to think of the same ballroom, but now let's imagine that we add one of the reagents. So a very confusing part for many people is the question why only the increase of one of the reagents changes the whole rate. Why shouldn't it be for the both of them? So let's kind of imagine that we increase one of the reagent concentrations. Let's imagine it to be the gentleman, and now let us consider some kind of a random motion of them. And if we consider the random motion of each of the individuals, now you can see that it is much more likely for the lady that is dancing in the ballroom to stumble upon the gentleman, and hence they can start dancing together much more quickly. If we consider this particular scenario in which there is two ladies and 6 gentlemen, there is of course going to be 4 gentlemen left without a pair. Well, we don't really care about it. If you think of it, it's more than intuitive. The reaction has already proceeded to the fullest. It cannot proceed any further. But it has proceeded much faster, because now it was much more simple for the lady to meet a gentleman and start dancing together, which indicates a reaction occurring. So the good question to ask right now would be, how is it encapsulated in mathematics? We, in chemistry and chemical engineering, love to portray things in a mathematical manner, and this is all captured in one simple equation, that the rate is going to be the rate constant times the concentration of the first reagent. So let's denote it as A in square brackets, raised to the power of its stoichiometric coefficient, which is 1 in this case, times the same for the second reagent, raised to the power of its stoichiometric coefficient. So the rate, for the people of that are more interested in mathematical aspects, we define the rate as the derivative of the concentration with respect to time. So for component C, it would be dc dt equals to K times A times B. So we can already see that the rate is going to be dependent on the concentrations, right? So we can denote very easily that rate is a function of concentration. This is something that we know from the very topic. But now the question is, where is this whole temperature part? We could already see that it doesn't matter what is the concentration for the temperature part, because temperature just influences how quickly the molecules move. So in this case, how quickly the dancers move. So it must be not a part of this concentration term. However, it must be somewhere hidden in this constant. And the thing with this constant is that it is only a constant for a certain temperature and a certain reaction. So it's a very specific constant. This is called the rate constant. Rate constant, and this is specific for T and specific for reaction. So if you look up the literature, for example, you might see that the rate constant for this particular reaction is equal to this and that for a certain temperature. And now what we know, what you can also see from your data booklet, is that this rate constant is actually re-expressed in this term, minus activation energy divided by RT. So we can immediately see that K is dependent on T, which also makes K a function of temperature. What does it mean for our case? Well, it definitely implies that rate is a function of both the concentration and temperature. Now we can also see that it will depend on the concentration in a polynomial kind of way, so in this power law, and on the temperature, it will depend in some kind of an exponential behavior. I hope this helped you to imagine how it works properly, how it can be thought of to make it more intuitive. I hope it also helps you in solving some questions, and good luck on your final exams.